Dear colleagues, the next speaker today is Tsanov from Sofia, the Institute of Mathematics and Informatics. Please, you have the floor.
Thank you very much. The organizers for inviting me here. Thank you all for being here. My talk is indeed not sharply on topics of concerns. I'll tell you the story of one family of varieties, algebraic varieties, which come out of the Planck manifolds, which were mentioned, but they undergo some modifications. And just as the Planck manifolds are important in actually various disciplines, so these varieties also play arguably important role. Though they're relatively unknown, and I hope that I and maybe other people will also find out interesting things about it. And in particular, maybe metrics could be of interest, though I'm not going to state any results on this. So let me say what I will be talking about. I'll be considering somehow as a central object, I'll consider embeddings of complex reductive algebraic and even linear algebraic groups, also connected. Later, I'll assume the big one to be simply connected, but this will be rather technical. And so I will study such embeddings from three different points of view. The first one will be the representation theory, which this is a very classical question. If you have an embedding of groups, this would be how to decompose representations of the large one under the small one. Because the groups are reductive and I'm discussing finite dimensional representations, they decompose into some irreducibles, so I can decompose irreducible representations of G over H. In particular, the space of H invariants inside an irreducible representation of G is of interest, and as I will mention further on, actually, if one understands the space of invariants for arbitrary embeddings, then one understands also the composition. So this is one thing, how to decompose representations. The other thing is how to study, so we can also act not linearly on vector spaces, but we can take a G variety, a homogeneous G variety maybe, and then look at the H-orbit structure. So H-orbit structure of, and I won't be looking at arbitrary G varieties, but on the Planck manifolds. Of G. So these are Cossack spaces by parabolic subgroups, and they constitute the projective equivariantly homogeneous spaces. of G. And the third point of view is the classifications or structure theory. So reductive Lie groups are classified by their ranking root systems and then fundamental roots. Infinitesimally, at least, they are classified by their root systems. Then further Dynkin. So actually, the famous Dynkin diagrams, they were not put up to classify the simple Lie groups, but to classify subgroups. Though just a diagram doesn't suffice to classify the subgroups, you get to decorate it and music. But anyway, these roots and weights theory can be extended to classify the subgroups. There is an article of Dynkin, huge tables. One can, in principle, use the classification to solve the above for this problem. Now, but of course, this is a crazy endeavor because the tables are large. But what one can do is use the notions that are used for the classification, for the study of the structure, and see how these notions relate to the above problems, and maybe consider types of subgroups according to their behavior here. For instance, if the dimension of this is always smaller or equal to 1, the subgroup is called spherical, and this is equivalent to it having an open orbit in any flat manifold G. And then there is a famous classification of spherical subgroups by Kramer in the reductive case. So these are the 3 points of view, and I want to somehow cook up a family of manifolds that corresponds to this. So, in what sense? So, let me now just talk about G for a moment and say what kind of structure I associate with the five manifold representations. Recall how the reducible representations are parameterized so that we can make something concrete out of these questions. So I will assume this one to be simply connected for technical reasons. The other thing just requires more notation. And I will take X to be the full flag variety. Variety of G can also be obtained as a generic co-adjoint orbit. And then if I, so B is a Borel subgroup and P will be a Heckman subgroup. So this is maximal solvable, or this is Heckman maximal torus. So if this tells you nothing, then this is the maximal subgroup which can be made upper triangular with respect to a suitable basis, and this is the maximal subgroup which can be made diagonal. And so when I have this data on this variety, I can consider, I can cook up equivariant line bundles by considering, by fixing lambda to be the character lattice of T, which is also the character lattice of B, because T is equal isomorphic to B modulo its commutator. So this is Z to some power, and inside it I have lambda plus, which would be the dominant weight with respect to B. example of GLN. These are just the functionals on the diagonal entries of the diagonal torus, and this is the case where they're ordered on prism. And so to an element lambda, one weight of B, I can associate a line bundle L lambda, which is by definition the equivariant line bundle where, so I have to tell how B acts on the fiber over the initial point, and it acts by the character minus lambda is the suitable convention that I take. And then I use the group to make an equivariant line bundle out of it. And so this makes an isomorphism between this lattice and the Picard group of X. So all line bundles can be made equivariant. This assumption comes. And now, if I consider the global sections of this, then this is 0 if lambda is not a dominant weight, this pose, and is irreducible if lambda is actually dominant. So this is my notation. So for the irreducible representations, with highest weight,
in the first thesis, lambda not belong to this lambda plus.
Oh, thank you. Thank you very much. So the statement is in every irreducible representation, this subgroup has a unique up to scalar eigenvector, and this is the character, and its character determines the representation up to isomorphism. And then the dual is also irreducible. We can compute its character, but that doesn't. And so once we have this, we also get a map from X. So this is an effective base point free line bundle, and we get a map from X to the orbit of the highest weight vector. The projective orbit is actually, well, the projective point is fixed for B. So this is why we get a map from G mod B to the projective space equivariant. And this is what is given by space of global sections, the standard projective. So if I need it, I'll denote it with P lambda. Right. And so, well, I can look not only at the global sections, but I can look at the ring R lambda. This would be, so the sum for J from 0 to infinity, the global sections, which, and I have to put power J here, but, well, this comes down to adding, so this power comes down here as a multiple of the factor. It can easily be deduced from this formula. And so we get the sum of all reducible representations. You can ignore the star. All reducible representations with a multiple of the given dominant weight as its highest weight. And so they form a ring very nicely. And on top of it, I can consider the Cox ring, which is, so I have this discrete Picard group, and I can consider just take all the line bundles. And then according to this, this will give me all the representations. And when I run over all of them, I can ignore the star. So I just get lambda in lambda plus. Everyone, just as in Peter Weil, they occur with multiplicity, they have representation, but over the applied variety, they occur without this. So I have every representation occurring exactly once. Here they are. So very nice thing. They form a ring if I add all. Well, and then, well, I wanted to study invariants. And then, well, if I consider the invariant ring in here with respect to H, then, I'll write it again. This is just, so all these invariants in the irreducible representations form nicely a ring. So, here is a question then. Does there exist, so if you know geometric invariant theory, something which I'll recall right away, one can ask, does there exist a variety y, it should be some quotient, of x, such that Fox y is Fox x H invariant. So can I make up a variety so that this is its Cox ring? And so what I will tell you today is that in most cases, almost yes. But so yes, in general, up to some fidgeting. And actually, the cases that are missed are exactly the spherical ones. Not exactly, but them and then a few more. But they are classified and well known. And so what we are able to capture is the generic case, which is otherwise quite difficult to study if you have encountered such questions. You know that one considers special classes of subgroups, symmetric subgroup, then you know the branching laws or the orbitals. But for a generic one, it is more difficult. And what we're looking at here is what's the situation rather with the generic subgroup. And what I wanted to recall is that somehow, why would one think of such a thing? It is, so in general, GIT tells us the geometric invariant theory, abbreviated standardly to GIT, tells us standardly that if I fix the lambda, I can find some q natural number so that sorry, I needed to introduce something more outstanding. What it tells us is that for one such ring, we can do it, but the question is how it works for the others. I'll recall how it's done for one. So if we take one of these, we can associate with the so-called unstable locus with respect to H with the parameter lambda. And this is the zero locus of the invariants. Well, positive degree the constants are not. Okay. So this is some algebraic subvariety of X. But careful, it may also be the whole of X, because may have no non-trivial. Then the semi-stable locus is just everything else. This is where the invariants do not vanish. And then when the invariants do not vanish, what I can form is the GIT quotient. So unstable locus, semi-stable locus, GIT quotient, where the equivalence relation is that X is equivalent to Y if and only if their orbit closures intersect in the semi-stable locus. So in general, one would like to consider the space of orbits, but this may not be Hausdorff, so we take only the closed orbits. Actually. And so now, when I have this, so GIT tells us now, I'll finish it over here, that there exists some Q so that and there exists a line bundle L so that well, the sections of X of L, and I can even put J lambda, the H-invariant sections, and I have to stick a number Q here. Maybe first I have to lift the line bundle to some power, and then for all its powers, I'll be getting exactly those. So, I mean, if you were to drop the Q, then we have that the invariant ring here is the ring of sections here, but thing is sometimes you need one.
Why is Y of lambda on the left? Is it quotient?
Yeah. So to every line bundle, we have this quotient, and then it inherits the invariants in its own ring. And what I'm asking for is actually, well, what about the other invariant? And well, I'm going to tell you in a moment what about the other invariants. But let me now, before telling you this, just introduce some notation about the lambdas and also give some relations to representation, to some known objects in representation theory. So this is the generalized Littlewood Richardson semigroup and form. So the Littlewood-Richardson of the embedding iota for short words, H-G. I'll put a 0 here. So these would be all the lambdas where invariants do occur.
So, what about the generators of current group of y lambda? Can we describe them using the current group of x?
Very good to get there, but yes, there are theorems. There is a theorem by Kraft and Bust, I think, which relates Picard groups of quotients to the Picard group of the original variety. And we do use this theorem in short. I just want to now gather some notation concerning. So I want to have a notation about all the lambdas that have invariants. We just introduce a few notions, So those that have invariants without a 0, so this is what should be the original Littlewood-Richardson, and I'll tell you why it's generalized. So the original one is for a particular type of embeddings. So these would be, so since I have two groups and you need parallel notation, the whole structure for all of them, H will be G tilde, and lambda tilde would be the character lattice of T tilde, which would be the, so tilde is the same sort of name of the letters. So these would be the pairs of dominant weights, so that from H V lambda tilde, I'll put a star here for technical reasons, into V lambda is non-zero. So these would be concerning the decomposition problem that I stated, but since this space is immediately written as V tilde tensor V lambda, and then H homomorphisms means H invariants. So this is again an invariant space. So this is actually LR0 of the identity times my given embedding dot. So in this sense, if you know how to find invariants for an arbitrary embedding, you know how to describe decompositions. You just have to consider embeddings of type identity times. Right. So, and the classical Littlewood-Richardson is for the case where G is equal to H to some power n, and then it's irreducible representations of G are tensor products of representations of H. And so we're looking at decomposition of tensor products, n copies, and then this is invariance in n plus 1. So this is to some extent the prototypical example. But I have so that I'm going to define also A. This comes from Apple. Well, I have these rings and these powers, and I have having invariants in the ring, somewhere in the ring. So I would consider those lambdas for which there exists some Q, so that I have invariants. the way this dualization, if I have invariance in the straight module, I have one in the dual, so the duality preserves this thing. So I have this, and I'll define, I'll put the convex half of this. So this is the code. Which is also equal to the convex half by the LR0. So this is the cone, little Richardson cone. It is rational, polyhedral, and convex. And it has been a subject of lots of studies, and it was described by Ressayre. So Ressayre gave a minimal list of inequalities. Before that, so some non-minimal lists were given before that by Berenstein-Sjamaar, and important steps were made by Heckman using compact groups and momentum maps to provide an equivalent formulation. This is what concerns the general case of arbitrary reductive groups. So for the diagonal case of SU, things have been designed according to inequalities, and by the way, so describing the cone is one thing. Then from the cone you have this, which is equal to the cone intersected with the lattice, basically. So describing this is one thing, these inequalities, and then finding the Q, by the way, which, because this semi-group is finitely generated, can be obtained as the least common multiple for generators. Finding the minimal Q such that Q times A belongs to LR0. This is called the saturation problem. And is one of the widest open problems that I know of in representation theory. So for instance, for this diagonal product, the case GLN is equal to 1, the saturation coefficient, but this was known as the Horn conjecture, and Knudsen and Gauss solved it with Woodward and works of Jachko and by other people, and the problem is not solved even for diagonal embeddings of simply latent conjecture, and the general case is really quite open. And I find this to be an interesting thing, and this also relates very well here. So this is also somehow everyone who has looked in geometric invariant theory has met this Q somewhere, and they always say there exists a Q. And so this is the lowest degree of an invariant. And I don't have an answer, but well, if I manage to get there, I'll tell you one way to approach this, at least for some cases. One doctoral student of mine solved it for SL2. So now that we have formulations of these things, I can introduce the GIT classes. So if I take two elements here on the prime, they're called GIT equivalent if and only if the unstable loci coincide. Certainly local would work, but also others, and so these classes, C lambda will be the class, is a rational polyhedral cone, and the classes form so now it is not rational polyhedral because I defined it for the discrete set, but because I'm allowed to take multiples, it can be defined for rationals, and then by continuity for reals, and so we get such classes in the cone. And the classes form a rational polyhedral fan in this cone. It's a further subdivision. Maybe this cone is not there. And now I have some special type of classes. So this is called the chamber. Chamber. If everything that has a positive dimensional stabilizer is unstable. So H X non-zero, this belongs to the unstable X. I'll be just writing lambda and it's always H on X. And is called H movable if the coordination is greater or equal to 2. And so, and I'll also denote CA or A and then so K of I to be those lambdas where this coordination is positive, is larger than positive, is greater or equal to K. So in particular, A is just A1 because having variance of positive dimensional unstable locus. A2 is called the movable cone. Move HX is by definition the cone on A2. And so the nicest thing you can have is a movable chamber. Why? Well, because then this relation of the Picard groups that you asked about becomes very nice. Because how would the Picard groups be related? Well, they have an equivariant line bundle, and the stabilizer at any point acts trivially on the fiber. you can descend to the quotient. This is why we have two definitions. And vice versa, from the quotient, you can pull back and you can extend by Hartogs if you have coordination at least two. Otherwise you have unstable divisors, so something will be lost. And so here is a theorem. Seppaenen me. So let lambda be such that C lambda is a movable chamber. Is an H movable chamber. Then the quotient Y is more green space. So these are big words that so for me, here this is something with finitely generated Cox ring and discrete Picard group. So the Picard group is a lattice, it says finitely generated Cox. They are called more green spaces because the Mori program apparently runs good on them, but I am not an expert on this. Like to learn more, but we have a finitely generated Cox ring, and this is what I'm after. And we have the following: that the Picard group of X, at least over R, if you prefer, is isomorphic to the Picard group of Y over R. This is the same lattice over the reals. This ample cone, the H ample cone of iota, is the pseudo-effective cone. The GIT chambers are the Mori chambers. So these are equivalent lattice of line bundles here that have the same projective image. The class of lambda is the Neff cone. The movable, so A2, is the movable cone here, which is the line bundles with stable base locus of coordination at least 2. And what is good for the representation theory, the invariant ring is, well, it's not everything, but it's a finite extension of. So I can get all of my invariants up to a finite extension, maybe which is lost in the various Q's that I'll get for the various ones, and I'm not always sure to get one, but I get it up to a finite extension. So it exists if I have a movable chamber. And as I said, so the Picard groups are related, and your question, if I don't have a chamber, the Picard groups are still related, but again, so if you have unstable divisors, they will be lost. So there will be a difference in the run. And then there are some further subtleties. Indeed, when you have unstable divisors, you have to look at some characters that appear there, and there is a modification. But there is an exact formula for the relation, based under some reasonable assumptions in a paper by Locke and Muster. But that's a nice case. And so now the question is, do we have movable channel? Well,
Sorry, so this movable condition depends on embedding as well, not on the page itself.
very well. And this is part of, I want to remove it. This will be the best. Or I want to remove, I want to remove the embedding. Yeah, that's your point. It would be best if you can guess just from the types of the groups. And actually you can. At least to, of course, up to some few cases, but to a large extent, one can. And let's see. So the answer will be yes, but let's try to get there. So there is a formula for the unstable locus. So somehow my attitude towards this is that actually this is to a large extent Seppaenen's theorem, but I have to verify some necessary conditions that were needed here to get the general idea. Then my aim was more to really verify this. So how to actually on these plugged varieties, they're fairly well known. So you can actually compute a lot of things very explicitly. And this unstable locus. So in general, by Hilbert's theorem, this is, so X is embedded into some PV lambda. P. So this is those points in X such that their H orbit has 0 in it there. Or those, so I'm going to rewrite this now in 1,000 ways, or a bit less, so that there exists some one parameter subgroup defined by some C in I, K, K in G, in H would be a maximal compact. So that e to the t c, so this has real eigenvalues times v goes when t goes to minus infinity to 0. So you can pull it to 0 with some one parameter subgroup. And so I'll just write it like this. And now I start writing the index. So with the direction, not this is one parameter subgroup with the direction. So these are the ones that C pulls to 0. And then by the conjugacy theorems, one can reduce to, well, first a positive Weil chamber. So TH plus. But then actually one can do better. So there is a stratification theorem, which in this case can be carried out explicitly. I'm not going to write down all the details, but in our article, which is now a couple of years old, there is an exact formula for the theorem stratification. We can write here, oh, and then I have to write H because I said, yeah. So now I have H, the unstable locus, and then I put C belonging to some capital C of iota, which is set finite set of so-called Ressayre one parameter subgroups. So I'd say it in words, these are the ones
for which there are one parameter subgroups of H, so that the corresponding parabolic subgroup of G is maximal among all the parabolic subgroups of G defined by one parameter subgroups. Okay. Something like you would have the maximal parabolics, but you don't take the maximal parabolics of G, you take the maximal parabolics defined by A. And then, well, actually, this set you can also write it very explicitly. This is a union of Schubert cells. It's nothing random. Schubert cells of G, and now H becomes more or less irrelevant. So, so this is C in this capital C, and then union over W in this is the Weil group of G, so that W lambda C is positive. One sign, strictly positive. So this is the Hilbert-Manford criterion. And then we take the parabolic subgroup, and I act on XW. So W is the Weil group. And the torus fixed points are the XWs, which is WB. I have to make a technical assumption here that lambda is strictly dominant, otherwise there is more tweaking. So this is a union of parabolic orbits. So now this doesn't depend on H very much, as long as I know those, and those can be gotten. And then I have to saturate. But now I know a dimension that the dimension of H peak C XW is less than or equal to the dimension of, so the tildes were the things of H. So this is a flag manifold of H plus the dimension of this. But this is a Schubert variety. The dimension is computed as length of some Weil group element. So these are very well-known numbers, and these are computable numbers. And now I have a limit. And then this is equal for stratifying elements, which can be detected by some recursive procedure. And so now I can compute the dimension very explicitly. There are combinatorial formulae for the dimension of the unstable locus. But this is what I want. Dimensions of unstable locus. So, now I can compute dimensions, and I have first the following. So I know now how my unstable locus looks like, and I can see when it will change, when one of these signs. Then there is the stratification. So I know that the T tilde, so this is the one of H, GIT-classes are defined by the hyperplane arrangement H script H WC for C Ressayre one parameter subgroup and W in W, small W in large. And then the H GIT-classes are obtained by deleting sum of the walls. And the chambers are the full dimensional ones. So I know the chambers, and then there comes the most curious thing, I think. So I know the GIT-classes, they can be computed very explicitly. The ones that have to be deleted, the walls that have to be deleted, this is done by a recursive procedure. It's not very easy to foresee, but doable. So I have the chambers. So what about movable? Here's the following. I think that this is the most interesting thing, the no jump lemma. If C1 and C2 are GIT classes in this ample code, then so that their neighbors, so their closures intersect. Then the codimension differs by at most one. There are no big jumps. So from 0 outside the ample cone on the boundary, you have 1, and so on. So coding with H C1 minus coding X is C2 H is less or equal to 1. In particular, this CK plus 1 iota is contained in the relative interior of CAK iota. So there is the boundary of the thing, then a layer of chambers, and then the next thing, and then a layer of chambers, and then the next thing. We call it economics. But so this is very nice. So in particular, if the third one is not empty, not 0, then movable chambers exist. Right, so we have a criteria, and then you can cook up a bunch of numerical criteria. For instance, you can look at the canonical bundle. For it, you can make some implicit calculation, and you can deduce that in most cases it has larger than 3, and you're done. But there is actually even more than that, and if you give me another minute, I'll tell you that actually in most cases everything is movable. So I define an invariant L lambda to be the codimension of this unstable locus with respect to G, the Cartan of G. And I define LG to be the minimum of the L lambda or lambda in lambda plus. And this has nothing to do with H. And then the theorem of Tsanov is that it's fairly easy, follows from these inequalities, is that LG minus the number of positive roots of H is larger or equal to K, in particular it's positive, then this CAK the fiota is equal to the voucher. So, is this weak or strong? Well, here are the values of this thing. And with this, I'll finish. So the type of G, then L of G. And so for type A or SLN, this is nothing, this is 1, 0, G. And I think this is why nobody looked at it, but for Bn, it is N. This is very useful because actually only some linear subgroups in here would have more roots. So basically, if you have a subgroup of SO SO odd, you're good. For Cn, the symplectic group, N again. For the odd orthogonal, the even orthogonal groups, N minus 1 if N is not 5, and 3 if N is 5. There is in this theory there is always the option. Spin 10, by the way, doesn't have any invariant polynomials. Then for E6, it is 5. For E7, it is 10. For E8, it is 29. This almost killed me. For F4, it is 8. And for G2, it is 3. And so this 1 is annoying, it's kind of useless, but you can just tweak it a little bit and say self-dual. So it wouldn't apply to all subgroups, but with some conditions. So this is the one which is for lambda equal to lambda star. So L S D G is the minimum of the L lambda for the self-dual weight. And then you get to N plus 2 over 2, which is the middle, and so now you get almost everything. And then, so this is the same, the 3 disappears and becomes N plus 1. And here, instead of the 5, you get 9. And for the other ones, it's equal. So the corollary is that if you have a subgroup H which is isomorphic to SL2 or E8, for instance, one easy corollary, then CA is equal to the Weil chamber and even movable for E8 if and only if G has no factors isomorphic to H. So the diagonal case, you never have this property. But this almost detects the diagonal is almost the only case when you don't have this property. For instance, for those groups. So if E8 acts on something, it has invariant. Always. Even has movable channel. And thank you for your patience.